most of you will be able to look at that and say, oh yes, I noticed, by inspecting this function, my brain just knows the gain of this transfer function is 2. There are 2 time constants. It's a second order transfer function. The 2 time constants are 3 and 2, and there is a 5-second delay. So effectively, I'm expecting you to say, right, there's a gain, there's a first order transfer function, there's another first order transfer function. Now these first order transfer functions have gain of 1 to make. So I'm expecting you to kind of mentally decompose this diagram into these parts. And then I'm expecting you, again, mentally to know what the gain and phase parts of each of those diagrams look like. Now these I do expect you to commit to memory. So I expect you to look at these and say, I know what each one of those looks like. I know that the gain part of these diagrams, that one looks like, I'm going to actually tabulate them below one another so it's easy to add, right? So the gain part is just a straight line at 2 for the first part, okay? The gain part of these first order transfer functions are going to be based on the time constant. They're going to differ because they've got different time constants. And they are going to have the property that the corner frequency is 1 over the time constant. So the corner frequency I'm talking about is that these diagrams, the gain part looks like this, and that frequency is 1 over 3, and that this frequency is 1 over 2. And you can see that 1 over 3 is a smaller number than 1 over 2, right? And the gain part of the dead time is just 1 all the way. Okay, so that low frequency asymptote here is 1, low frequency asymptote here is 1. A useful thing to know about 1 is that the log of 1 is 0. Okay, and so when we plot these on a decibel scale, you'll see these 1 unity gains being at 0. If you just plot it on a log scale, it'll just be at 1. The scale will just be logarithmic. So when we now want to calculate this product, because the log of a product is the sum of the logs, right? That's log rules, okay? Because of that, we can just add all of these things together. Again, I'm expecting you to add them mentally in your mind so that you end up with a combined gain part that is, now again, when we're talking about these, you've got to reason logarithmically, right? So the gain part will be at 2. Does that make sense? The shape is adding together. Another way of thinking about this is like I'm taking the log and then adding all those things in the logged domain. So these unity gains don't have an effect, right? So the overall gain will be 2. And then there'll be these 2 corner frequencies, the one at 1 over 3. And that slope is like -1 per decade. This is -1 per decade. So this will be minus 1 per decade up to that frequency, at which point it will go to -2 per decade. Okay, you kind of loosely say that's what the actual Bode diagram will look like. It'll kind of interpolate onto those curves. Then similarly, phase part, similarly over here, I'm expecting you to know constant gain has a 0 phase angle, that the first order systems both have this kind of thing that goes from 0 to -90 degrees, and that the dead time starts at 0 but then just goes off and it kind of goes infinitely down. Dead time has infinite phase because it kind of unwraps as it goes along. And so again, mentally, we're just going to add those together, and we'll end up with something that starts at 0. Again, these frequencies here are the same thing, 1 over 3 and 1 over 2. And so we'll start with something that has kind of these two little bumps and then keeps going down. Okay, now again, keep in mind that what I've drawn here is like a cartoon, right? Like it's not actually what it looks like. So we put these two together, and by convention, we put them together in this kind of Bode diagram form. So we've got the gain part, and we draw in these two. Now again, I'm drawing this like not to scale, right? Like 1 over 3 and 1 over 2 aren't necessarily exactly where I've drawn them over here, but they are in this order of that gain part, and kind of this eventual frequency here will be -2 per decade. That's I've drawn the smooth curve, right? I've drawn the curve that looks like it would actually look if you drew it on the computer, but the asymptotes are something like this. Okay, now that's very approximate, but what I'm trying to draw here is you can see that a couple of things. The asymptotes are not guaranteed to touch the real actual graph. That's the first thing, right? So the asymptotes, and they have less of a likelihood of actually touching the closer these parts are together, because we're reasoning asymptotically about the slopes. And the phase is even kind of worse. It doesn't necessarily follow the same thing, but again, so we see here that that asymptote is -1 per decade. It starts there at 2. It kind of starts out flat in the low frequency asymptote, and now the two parts that are 100% guaranteed real, correct, right, are the very low frequency behavior and the very high frequency behavior, because how did we get the asymptotic behavior? We got it by taking the limits, right? So we got the asymptotic low frequency behavior by taking the limit as s goes to 0, and we got the asymptotic high frequency behavior by taking the limit as omega goes to infinity. So we trust those points much more than any of the other points. And so we know that kind of at approximately -90 degrees, there's kind of this inflection point there, there's another one there, and then this goes down all the way. Okay, so I also expect you to be able to operate this machine cranked in the opposite direction, right? How would I know from looking at this? Because this is the opposite question, right? The opposite question is, you know, some kind of blurb at the top. Plant personnel have determined that from testing of some kind, by using whatever, they have developed this graph. What is the transfer function of G? Okay? Now, you can easily work backwards for at least 3 of the components. You can probably observe the corner frequencies. If I'm giving you this, they'll be visible enough as kind of the points at which slopes change. You can kind of construct straight lines like this. You can definitely construct a straight line from the bottom frequency and from the top frequency. This middle one, you've got to kind of guess. But you know that they go in unit amounts of slope. Right? So if you were working with normal transfer functions, the slope only changes in these -1 per decade increments. And you know that the phase also does the same, but in -90 increments. And so you can look at this and say it's got to be a net second order system, because the asymptotic high frequency behavior goes down at -2. Right? So that tells me second order system. It's got to have, it looks like that dead time, or it looks like that phase is just going crazy. So it's probably got dead time, right? And so the first thing you do is you say, okay, I can look at this and infer that this is going to be of this shape. So how did I do this? I looked at the asymptotic behavior over here. I noticed that this was like steady, so it's a straightforward system with behavior that goes to a constant when s goes to 0, right? I can read that constant off in that low frequency asymptote, right? So I can say this allows me to see that gain is 2. Okay? I can read off from these inflections what the time constants are. And the only reliable way of actually knowing the dead time is to take all of that known knowledge that I have already and then calculate the dead time based on a measurement that I've made in the higher frequency area of, like, I can see, okay, at this particular frequency, the phase is exactly this. And I can then back calculate for the dead time.